Continuity and one-sided limit, Part 2.
Let's say that we want to look at some parts of a function, not the whole thing. Then there would be endpoint. How do we define continuity on a closed interval with the endpoint? So look at the graph below. If I'm only looking at this function f from interval 1 to 3, my graph only has part, and there will be endpoints right here and there. So I will not have any graph on the left-hand side of 1 or right-hand side of 3. So there will be no left limit x approach to 1 of f of x, and there is no right limit of f of x as x approaches to 3. So this is how we define continuity on a closed interval. First, as far as fx is continuous on open interval a to b, so there is no gap, no jump, and no hole in between the endpoints. And we only look at right limit of a because there is no left limit of this function. And as far as that's equal to this function value, and this time you only look at left limit of this function as x approach to the endpoint, which is a b. And as far as that's equal to the function value, then we say this function is continuous on the closed interval a to b. So we're actually gonna use numbers and looking at this function and decide whether this function is continuous on the closed interval 1 to 3. So 1, you can just quote, since this function has no hole, no gap, no jump between 1 to 3, fx is continuous on open interval, in this case 1 to 3. Number 2, limit x approach to 1. So I only can talk about limit from the right of this f of x is equal to, you can follow your graph and say what's the limit is, and you can see limit is 2. This is 2. And what's f of 1? Because that's gotta be equal to the function value, right? So f of 1 is equal to, since this point is f of 1, it is 2. And yes, they do matches. Number 3 condition, the other endpoint is 3. And as x approaches to 3 from the left this time, because we don't have any graph on the right hand side of 3, of this function is equal to, and you can try to get closer as x approaches to 3 from the left. The limit is, you can see, 4. And f of 3, the function value at x equal 3 is indeed 4. And because it satisfies all 3 conditions here, you can say f is continuous on closed interval 1 to 3. Name the intervals on which each function is continuous. So let's look at first function h of x. H of x is continuous on open interval 1 to 3. There's no jump, no gap, no hole between 1 to 3. Number 2, how about the starting point 1? So what's the limit? X approaches to 1 from the, we only have the right limit of h of x, and the right limit is 2. And is that equal to the h of 1? H of 1 is this point, 1, 2. H of 1 is 2. So yes, so this function is continuous at 1. Now how about the other endpoint 3? What is the limit? X approaches to 3 from the left. This time we only can go from the left, right? So from the left of h of x, get closer, closer, closer to 3. Oops, where is it going? It's going to infinity. And infinity is not a number. We say limit does not exist. And obviously, we don't even have h of 3 either. H of 3 is undefined. And h of 3 does not exist. So this function, h of x, is continuous on closed interval because the starting point 1 is good. It continues from 1 through 3 but 3 itself wasn't included in point of continuous. Second question, let's look at f of x. First, we can see f of x is continuous on open interval 1 to 3 because I can see in 1 to 3, graph has no gap, no jump, no hole in between 1 to 3. Now second, how about at starting point? Limit x approaches to 1 from the right of f of x. I get closer to 1 from the right. The limit is 2. But what is f of 1 though? F of 1 does not exist, right? I have a hole there. F of 1 does not exist. So this function is not continuous at 1 because f of 1 does not exist. What about the other endpoint? You can see same thing happens here. Limit x approaches to 3 from the left of f of x is, what is the limit value, guys? Limit is 4, right? Limit is 4. But again, f of 3 does not exist. Therefore, this function is not continuous at 3 itself either. So, since it says name the intervals on which this function is continuous, you can conclude that f is only continuous on where you stated at the beginning, continuous on open interval 1 to 3 only. That will be your conclusion. Lastly, let's look at g of x now. Is g of x continuous on open interval 1 to 3? There is a hole. So g of x is not continuous at this point because there's a hole in there, okay? Because g of 2 does not exist, right? So g of x is continuous. Then where? It was fine here to there, and it was fine here to there. So you can say g of x is continuous on open interval 1 to 2, union open interval 2 to 3. And how about the endpoint 1? Okay, limit x approach to 1 from the right of g of x is what? If you get closer to 1 from the right, then limit is 2. And that is equal to your function value, right? Because you do have a function value there, which is g of 1, and g of 1 is 2 since this point is 1, 2. And how about the other endpoint as x approaches to 3 from the left of this function? Limit is 4. And you do have a function value here too. This is a 3, 4. So g of 3 is also 4. So at 3, it is continuous. Conclusion, g of x is continuous on closed interval 1 to 2. However, function is not continuous at 2 because f of 2 does not exist. So union 2 not included 2, 3 is included.
Next one is very important first theorem of calculus. Intermediate value theorem. You can use abbreviation. We use IVT for intermediate value theorem. In order for intermediate value theorems to apply, the following 3 conditions has to be met. So first of all, fx has to be continuous on closed interval AB. You must state that in order to use this theorem. Second thing you have to check is f of a cannot be equal to f of b in order to use IVT. Number 3, k has to be value between fa and fb. It has to be in between fa and fb in order for you to apply the IVT. If these 3 conditions are met, then for any k you choose between FA and FB, let's just say I choose this one. So let's just say you have a continuous function like that on closed interval a to b. All right, that's the number 1. And then here's f of a. And here's f of b, so you can see f of a is bigger than our f of b value right now. And if k is any value in between f and a and f of b, then it's saying there has to be a c inside of interval a to b such that f of c equal k. Why does that has to happen? Because function, we just said, is continuous in the closed interval a to b. But the f of a is up there, f of b is down there. And in order for this function to be continuous, meaning connected from fa to fb, it's gotta take up all the function values in between. So you can choose any k and there has to be a value. You can choose this one. There is actually 1, 2, 3 values of c such that f of c equal k. So that's why it says there exists at least one c. It could be 1c, 2c, 3c's, but it has to be in that interval of AB. So make sure you also, when you're doing problems, such a c you found is in this interval A to B. That's critical as well. Let's go ahead and do what kind of problem we could do with IVT. Use the IVT to prove f of x equal x cubed plus x minus 13 has a root in the interval 2 to 3, or explain why it fails. When the test fails, you simply say that IVT does not apply because condition didn't met. That's all conclusion you can draw. So here, let's check the first one. fx is x cubed plus x minus 13 and it's a polynomial. And you can use or quote that every polynomial is continuous on all real numbers. I'm gonna say since f is continuous on all real numbers, it is also continuous on closed interval 2 to 3. You don't have to really. Number 2, we gotta check endpoints. What's f of 2? F of 2 is 2 cubed plus 2 subtract 13, which is equal to 8 plus 2 subtract 13, which is negative 3. And then what is f of 3? F of 3 is 3 cubed plus 3 subtract 13, which is 27 plus 3 subtract 13. So that's a 30 minus 13, which is 17. So clearly f of 2 then is not equal to f of 3. And then they said prove that it has a root. So guys, if this function has a root, then what's the function value of a root? Function value of any roots are the x values such that y values are 0. So the k that IVT was talking about in the theorem. Let me show you the previous screen. So K is between FA and FB. So right now, my f of 2, so here's a 2. F of 2 is negative 3. This is negative 3. And f of 3, so at 3, it is 17. So 17 is way up there, let's say. This is 17. And this function is continuous. So it's asking, prove that there is a root. And what is the function value of this root? That will be 0, right? And it's 0 between negative 3 and 17. Yes. So the k here that IVT was talking about is 0 because, the function value of a root is 0. And 0 is between negative 3 and 17, which this is f of 3 and this is f of 2. So thus, what can you conclude? IVT applies and there exists. Guys, this is the symbol means there exists. You can literally write out, but every time you see this backwards E, it means there exists. There exists a C in the interval 2 to 3 such that f of C equals 0. But this means that what? This function has a 0 or function has a root in that interval. So we just proved it. Use IVT to prove fx equal x cubed plus 2 over x minus 4 has a root in the interval 1 to 2, or explain why it fails. This is a rational function. And what do you know about rational function? Rational function is continuous on its domain. And what is the domain of this guy? This domain is negative infinity to 4 union 4 to infinity. It's all real number except 4. And this is inside of this interval. Since f is continuous on negative infinity to 4 union 4 to infinity, it is continuous on closed interval 1 to 2. What is the number 2 condition for IVT? Yes, the endpoint, the function value has to be different. So let's calculate f of 1. F of 1 is 1 cubed plus 2 over 1 minus 4, which is equal to 3 over negative 3. So I get negative 1. And f of 2 is equal to 2 cubed plus 2 over 2 subtract 4, which is equal to 8 plus 2 over negative 2, which is now negative 5. So f of 1 is not equal to f of 2. Now, but it says prove that this function has a root in this interval. But root function value is 0. Is 0 between negative 1 and negative 5? No. So what do you say? But 0 is not between negative 1 and negative 5. All you have to conclude is that IVT does not apply. Or you can say IVT fails, right? You don't say, oh, therefore the root does not exist between negative 1 and negative 5. We do not know that, because I could have function value to be at 1, it's negative 1, and at 2, it's a negative 5. But it could have done this, but we just don't know. Is that right? So you could not say that. Don't say that the root does not exist. You just say IVT does not apply, meaning we do not know whether root exists or not. All right, just so that you know how to say this. This time, find actually the value of C guaranteed by IVT for this function on the interval 0 to 3, where f of C equal 5 over 8. Or explain why it fails if it fails. Okay, so again, let's try to see if even IVT applies. So this is a rational function, and rational function is continuous on all real numbers except negative 6 for this case. So you can say that since f is continuous on negative infinity to negative 6 union negative 6 to infinity, and closed interval 0 to 3 is in here, so it is continuous on closed interval 0 to 3. Number 2, what's f of 0? F of 0 is 0 squared plus 1 over 0 plus 6, which is equal to 1 over 6. And what's f of 3? F of 3 is 3 squared plus 1 over 3 plus 6, which is equal to 10 over 9. And then here is the k. We needed to prove that there's a c exists such that FC equal 5 over 8. So this is the k that they're talking about in this IVT theorem. So it's 5 over 8 between 1 over 6 and 10 over 9. Yeah, 5 over 8 is obviously bigger than 1 over 6. And then it is smaller than 10 over 9 since 10 over 9 is bigger than 1 and 5 over 8 is less than 1. But 5 over 8 is bigger than half and 1/6 is less than half. So we can clearly see this applies. So therefore, what can you conclude? Therefore, intermediate value theorem applies and there exists at least one C in that interval, given interval 0 to 3, such that f of C equal 5 over 8. So what do we do now? You just plug C into your function, set that equal to 5 over 8, and we find such a C. So let's go ahead and plug it in. It is C squared plus 1 over C plus 6, which is equal to 5 over 8. And how do you solve that? You can cross multiply and set them equal. So then you will have 8 times C squared plus 1 equal to 5 times C plus 6. It's quadratic now, right? So it's 8C squared plus 8 equal 5C plus 30. And then since it's a quadratic, let's set it equal to 0. So you get 8c squared minus 5c. 8 minus 30 will be negative 22 equals 0. And let's go ahead and factor it. I think it will work with 8c times c. And then in order for me to get negative 5, I need to have 2 here and 11 there. And I need this to be negative, so that's going to be negative 16c. I need this to be positive, so this is positive 11c. That will give me negative 5c. So factoring become 8c plus 11. C minus 2 equals 0. So then first C could be negative 11 over 8. Second possible C is 2. But remember, I need the C in this interval. So this you need to disregard. And such a C that is guaranteed by IVT will be C equal 2. All right. Guys, this is very important problem. I can almost guarantee that this will be on the test. Of course, problem's not gonna be exactly the same, right? Slightly different. And this is every work you need to show on the test, okay? All right, guys, good job. And I will continue with 1.5 soon.